Example 89, leaky bucket. So here we have a bucket with water in it, and there's a hole over here, and the water is leaking out. Okay, so we can use Bernoulli's equation and continuity equation to solve the question. It says, at what speed does the water emerge from the hole? Okay, so here we've got point 1, there's 1, and there's point 2. So what is Bernoulli's equation? P1, pressure at 1, plus rho g y1, plus half m v1 squared is P2 plus rho g y2 plus half mv2 squared. Okay, alright, so let's now apply this. So here we've got the velocities, the speeds, so we can use this equation. There's a difference in height. Okay, so let's now apply this. What is P1? P1 is the pressure here at the surface, and that is just simply going to be P atmosphere. Okay, so we've got pressure atmosphere there, but also because the fluid is, or the water is flowing out into the atmosphere, pressure 2 is also P atmosphere. Okay, so P1 and P2 are the atmospheric pressure. Okay, rho gy. So y1 is just simply, if you measure from here, y1, and there's y2. Okay, so there's y1, you just measure y1 from some arbitrary, remember guys, does it matter where you're measuring it from? No, because we are dealing with differences. If you measure from down here all the way to the top and down from the same reference point all the way there, you're just going to be calculating this difference d. You see y1, y2? So it doesn't matter where you measure from. Actually, you could probably even just measure from there and measure that distance d, right? Anyways, you can play around with that and make sure that you understand that. Okay, so we've got y1 and we've got y2. So we've got these two terms. We've sorted out the pressures. Now, this is one thing that maybe is not so obvious, but velocity 2 is much greater than velocity 1. So the speed over here of the water that's slowly moving down is much slower than the speed of the water flowing out the small hole. So we can assume that our velocity, our speed 1, is 0. Okay, so we can, it's an assumption. For practical purposes, we assume that speed 1 is 0. So we've got, so we're looking for speed 2. Now, because P1 and P2 are both atmospheric pressure, they also can fall away because it's the same value. P1 equals P2, so they fall away. So what we're left with is this: rho g y1 plus half rho v1. I see I made a mistake here. This should be a rho. Sorry. Okay. Half rho v1, and remember this just falls away, equals rho g y2 plus half rho v2 squared. Dividing through by half rho and setting this one equal to 0, we end up with this. We solve for v2, which is the root of 2gd. Okay, so the velocity here is a function of the distance between the 2 points, but it's a function of the square root of that distance, and it's the square root of 2gd. Now, where have we seen this before? Where have we seen this before? Well, if your equations of motion, v squared is v original squared plus 2gd delta x, right? Your equation of motion. So for an object that's freely falling, the original velocity is 0, so that goes to 0. And if you solve for v, you get v is the square root of 2g delta x, which is simply just your distance. So my answer, or his answer, is equal to the speed acquired over a vertical distance d by a freely falling object starting from rest. Okay, so it's the same as a freely falling object, the velocity.